Welcome to the third part of Lecture 3 on radioactive decay kinetics for Chem 418. For Lecture 3, Part 3, we're going to discuss reaction cross-sections, describe probability of reactions to occur. We're going to discuss the term cross-sections, which we've already talked about when we discussed the chart of the nuclides. Then we're going to explore natural radiation. We've already talked about natural radiation. We've looked at the uranium-238 decay chain in a previous lecture. And then we're going to end this on dating materials that contain radioisotopes, so how we can get information about age of materials. The cross-section is used in equations to calculate reaction rates. You can think of the cross-section as the probability of a reaction
to occur.
And it's a term that we've already discussed.
The cross-section symbol is sigma, and some values for reactions with neutrons can be found in the chart of the nuclides.
For example, this tellurium-130, there's cross-sections that go from thermal neutron, resonance neutron, to the metastable state, and then thermal resonance to the ground state. These values are described within the chart of the nuclides. So it's a term we've already discussed, and it has a dimensioned area. It's 10 to the minus 24 centimeters squared is the value for the cross-section, which is called a barn. And barn value is strange unit, right? 10 to the minus 24 centimeters squared. Well, a nuclear radius is around 10 to the minus 14 meters squared. If I took the area pi r squared, I'd get a dimension that would be on the order of 10 to the minus 24 centimeters squared. Now, this value originates from the probability of a reaction between a nucleus and a particle, and it's proportional to the physical cross-section of the area presented by the nucleus. This isn't completely true. For instance, with a charged particle, you have a Coulomb barrier to overcome. With slow neutrons, you have resonances that are based upon some quantum mechanical properties. Basically, a general trend would be that the reaction cross-section is going to be fundamentally proportional to the area that the particle can see from the nucleus. And this is really true. If you have fast particles, the cross-section is never greater than twice the geometric cross-section of the nucleus. Cross-sections for fast particles tend to be close to a barn. It also depends upon the exact reaction that you're looking at. And what we're going to see when we explore cross-sections is that we'll have some cross-sections which are close to a barn, seem reasonable, and then some cross-sections that are multiple barns, thousands of barns. So in essence, it's as if the nucleus expands. That's not what's really happening. Quantum mechanics comes into play, and you have wave function overlaps that increase the probability of reactions. So let's see how cross-section can be used in some reactions. The cross-sections that are in the chart of the nuclides are for neutron reactions, and the sigma that represents the cross-section will have a symbol next to it, a gamma or a F, gamma for just neutron capture, F for fission. We'll explain this in more detail when we discuss those different reactions. But there's also cross-sections for accelerator reactions. So in an accelerator reaction, a beam of particles strikes a thin target with a minimum beam attenuation. So the energy loss as the beam travels through the target can be neglected for this equation to be valid. And that's important because
for accelerator-based reactions, the cross-section is a function of the projectile energy. For a given reaction, the change in cross-section with energy is called an excitation function, and we will discuss this in more detail later in the course.
So we have these terms where we have the incident particles per unit time, a beam current. We have the number of
target atoms
per centimeter cubed. We have a target thickness in centimeters, so we see that we get an inverse centimeter unit here. And then we have the cross section, which is in centimeters squared. So we see that the area values get removed. For reactors, we use a different equation, and we assume that a particle,
in this case the neutron, has
a uniform flux, is impinging upon a target and cross section
for a given reaction with the target isotope.
So we've got the rate of reactions some sort of processes just over here, how many reactions are occurring per unit time, is equal to the cross-section times the number of nuclei that are in the sample times the flux. So that's particles per centimeter squared per second. And this is a property, this flux is a property of the reactor. This target, that's the property of the target that you're putting in. And this is the cross-section that one can find. Of course, if I had an unknown and I measured the rate of the reaction, the rate of the process, and I knew something about the reactor flux, and I knew the number of atoms that were in the target, I could figure out the cross-section. And if I had an unknown reactor and I wanted to measure its flux, I would put a target that's known in with a cross-section that's understood, measure
The reaction rate.
and I could evaluate the flux. So these equations provide us an opportunity to evaluate terms and processes in nuclear reactions. Those equations that I showed in the previous slide are fundamentally correct. However, we are neglecting an important consideration, and that's the decay of any isotopes that are produced while the production is ongoing. And we need to consider something a saturation factor.
In the previous slide, we discussed rates of formation. Another way of evaluating these rates of formation is shown here using this equation, where if the activity of an isotope is measured after the reactions to produce that isotope, and that activity is divided by this saturation factor, 1 minus e to the minus lambda t, that'll provide the rate of formation. And that should be the same rate of formation value as calculated from the equations on the previous slide. Since the measured activity divided by the saturation factor yields the isotope formation rate, one could evaluate cross-sections, fluxes, and target information using experimental data from an irradiation, as we discussed in the previous slide.
But let's think about what this saturation factor means. As one is producing an isotope, when it's made, it also has a probability of decaying.
If the isotope is stable, this probability is 0. Otherwise, it is based on the half-life.
So if you're producing an isotope that has a half-life of 100 years, and you're producing it in a reactor,
and that reaction takes an hour,
the probability that one of the atoms you made that has a half-life of 100 years decaying within that hour is pretty small. So we don't really need to include the saturation factor. However, if you're irradiating a sample for an hour and the half-life of the isotope that you're producing is 3 hours,
a measurable amount of that isotope may have decayed.
And you need to include this saturation factor.
Using the saturation factor, the number of product atoms produced is equal to the number of target atoms times the cross-section times the flux, as we discussed on the previous page, divided by the decay constant for the atom produced times the saturation factor, 1 minus e to the minus lambda t, where lambda is the decay constant for the isotope produced. If the number of product atoms are known, the activity can be found by multiplying the number of product atoms by the decay constant. And all we need to do is rearrange this equation.
The activity of 1 is equal to the initial amount of target times the cross-section times the flux, same equation as we used in the previous page, multiplied by 1 minus e to the minus lambda 1t. So this is the decay constant of the isotope that you're producing.
This term, 1 minus e to the minus lambda t, is called the saturation factor, and it
gives you an idea of where you're going to reach a maximum level. As one continues to irradiate, and if I look at the amount of half-lives of the daughter, and I compare that to the irradiation time, I reach a level where longer irradiations does not produce more material. This is because over here, as let's say within one half-life, it's fairly linear. Some of the atoms that have been produced have decayed because the atoms are being produced over this entire half-life time. So the ones that were initially produced at the very beginning of the reaction have a 50% probability of decaying, while those at the end have a very small probability of decaying. But as I increase this, more of the initial atoms have a probability of decaying because they're experiencing many half-lives. And you just reach a point around 7 half-lives where fundamentally reached an equilibrium that you're producing more from a reaction, but you're losing those atoms that were made earlier. So this tells you that if you're doing a production reaction, you should never go more than 7 half-lives of your isotope. So if I was making an isotope that was an hour, anything more than 7 half-lives is not worth it. In fact, you can make an argument that, well, the amount that I gain from 4 to 7 is pretty small. 3 to 7 is pretty small. From 2 to 7, I'm only gaining 25% more. So one could evaluate that. Is it really worth that extra time to produce a relatively small amount of material? So we have these saturation factors, and as a function of half-life, you can see what sort of percentage of the saturation you're reaching. Let's compare these two equations in two different scenarios. One where the irradiation time is short compared to the half-life, and one where the irradiation time is long compared to the half-life. So for our first example, let's use a reaction to make iron 59, this isotope, 44.5 day half-life, from iron 58. We'll add a neutron to the iron 58. It will absorb that neutron, give off a gamma, and make iron 59. It gives off the gamma because it makes an excited iron 59 state. That photon makes it decay to the ground state. So it's just a simple transition. And we see that as this N, gamma, iron 59. So target, projectile, reaction product, reaction product. Another way of writing it is shown here. We'll go over more detail about this reaction later in the course, how we this sort of nomenclature. But we can also write it as iron 58 plus a neutron goes to a photon plus iron 59. The cross section we can get right from the chart of the nuclides. It's 1.3. I write it here 1.3 times 10 to the minus 24 centimeters squared, because remember it's in Barnes, so this is in Barnes, and 10 to the minus 24 centimeters squared is our Barnes unit. So let's take our equation that we have here. We want to get N, right? We want to get the number of atoms that are sitting in the target. I state that there's 1 gram of iron. The molecular weight of iron is listed here. We use Avogadro's number. So now we've got the number of atoms of iron. And then I'm going to use this value because this is for iron. I didn't say any sort of enriched iron. I just said regular iron. And 0.282% of iron is iron 58. So I need to normalize it by that. And I get the number of targets as 3.04 times 10 to the 19th atoms. All right. So we've got our information. We've got our flux, which I provide here, a neutron flux. We've got the number of atoms, and we've got the cross section. So let's plug this information in to the equation. Flux, number of target atoms, cross sections. I get a rate of 3.95 times 10 to the 8th atoms per second. I say I want this irradiation for an hour. So there's 3,600 seconds in an hour. So from this, I get 1.4 times 10 to the 12th atoms of iron 59 are made in 1 hour. Now this reaction does not include the decay of any iron 59 that's during that hour of production. Let's include that by using the saturation factor. So the same terms that we used in this equation, we got to add something about the decay, so we got to bring in the decay constant. I provided the decay constant here, but it's just log 2 divided by the half-life, but this is all in seconds, so make sure if you were to do that yourself, you would convert days into seconds. So we use this equation. Let's plug in the terms, the number of iron 59 atoms that are made. is equal to the number of target atoms times the cross-section times the flux divided by the decay constant times 1 minus e to the decay constant times the time. That's where our time, that's the only place where the time really comes in. And this is basically providing a saturation factor. It says what percentage of the material is available. And what we get is a value that's shown here. We get 1.4 times 10 to the 12th atoms. We got 1.4 times 10 to the 12th atoms. And it says, you see, you need to go down to the fourth significant digit in order to see a difference. And as we would expect, this value would be less than this value. So this shows that, you could use either equation if something is relatively long-lived. If you have a spreadsheet that's set up and you're inputting the data, it doesn't really matter which equation you use. They would both equally well describe the reactions. All right, let's consider a condition where the radiation is relatively long compared to the half-life. So let's take the formation of manganese 56 from manganese 55. Again, a neutron capture reaction. So manganese 55 captures a neutron, gives off a gamma, makes this manganese 56. The half-life of the manganese 56 is 2.6 hours. We'll do an hour irradiation. So when we say that the radiation is long compared to the half-life, doesn't necessarily need to be longer than the half-life. It just needs to be a good fraction of the half-life in order for the saturation to come into play. All right, so let's get some of the data. Our cross-section for the manganese 55. So remember, the manganese 55 is absorbing the neutrons, so you need that cross-section, not the manganese 56 cross-section. We have our cross-section is 3.3 times 10 to the minus 24 centimeters squared. It's 13.3 times 10 to the minus 24 centimeters squared. The 13.3 Barnes value is listed here. Again, this is for thermal neutrons. You can assume I'm using a thermal neutron flux. This is for epithermal neutron flux or resonance energies, resonance neutron flux. If it's unclear in a question, you're free to use whichever one you want. I will try to specify, for instance, radiation from thermal neutrons. We have our data, right? We need to get the number of manganese targets. Said there's a gram of manganese. All of manganese is iron 55. The molecular weight of that all manganese is manganese 55. The molecular weight of that manganese 55 is listed here. So we have a way of calculating the number of manganese targets from 1 gram. That's sitting in the neutron flux. Let's use our equation. Let's input the terms. The rate is equal to the flux times the cross-section times the number of targets. We get a rate of 1.45 times 10 to the 12th atoms per second, 3,600 seconds in an hour. We get a value that we should make 5.24 times, or 5.25 times 10 to the 15th atoms of manganese 56 in an hour. Now remember, this equation does not count for decay. Let's consider decay. We use this equation where we have the saturation factor along with the decay constant. Let's plug those values in and let's solve. We get a distinctly different value. We get 4.6 times 10 to the 15th atoms. So this is a demonstration that if you are producing an isotope that's relatively short-lived, where the irradiation time is long compared to the half-life, you need to definitely include the saturation factor for accurate assessment of the amount of atoms that would be produced. We introduced this equation a few slides ago, where we can determine the formation rate based upon a measured activity and this saturation factor. So let's look at the example from the manganese 56 that we provided in the previous slide. We've gone through how we determine this value. Our activity, if I know the number of atoms of manganese 56, the decay constant, all right, so activity equals lambda n. I I have that value. I get so many becquerels, so 3.4 times 10 to the 11th becquerels. That's my activity. I substitute the activity into 1 minus e to the minus lambda times the time, and I get a production rate. So this production rate includes it's the overall production rate, and it does include the decay as a function of the irradiation time.
Equations that show the production of isotopes from accelerators were also provided, and we're going to show an example of that using the production of astatine-211 based upon conditions that are used at the University of Washington. The equation that was used is shown here, and the components of this equation, as a reminder, include your beam current, which ultimately is particles per second, so it's the projectile particles hitting the target. And then target information, which includes the atom density, so atoms per centimeter cubed, times the target thickness, that'll get centimeters squared. And then we get the cross-section, which is shown here from experimental data. And this cross-section for this reaction is about 1,000 millibarns. So that's 1 barn. And we'll use that as the cross-section. And remember, that's in 10 to the minus 24 centimeters squared per barn. So the data that we need to accumulate to run this equation is the same if we go for the equation that does not have the saturation or the equation which does have the saturation. The only addition for the saturation equation is the inclusion of the decay constant. And again, just like the reactor example that we showed on the previous page, if we know the activity and divide that by the saturation factor, we will get the production rate. So for the production of astatine-211, which is used as a radiopharmaceutical, the reaction includes a bismuth target, a helium projectile, 2 neutrons come off, and the product nuclei astatine-211 is produced. The helium target is a monovalent helium beam, and at 30 MeV, it has a beam current of 70 microamps for this accelerator. The unit ampere is used to convert the microamps to charges per second using the conversion that 1 ampere is equal to 6.24 times 10 to the 18th charges per second. And since the helium projectile is monovalent, 1 helium projectile is 1 charge. So from the 70 microamps, you multiply that by 6.42 times 10 to the 18th charges per second per amp, and you get 4.37 times 10 to the 14th particles impinging on the target per second. For the number of atoms per centimeter cubed, the target is metallic bismuth. Assuming 100% density of your target, use the density of bismuth, which is shown here to 9.7 grams per centimeter cubed. Convert that to atoms using the atomic mass of bismuth and Avogadro's number. You get 2.808 times 10 to the 22nd bismuth atoms per centimeter cubed. So that's the number of targets per centimeter cubed. The target thickness for this example will be 0.1 centimeter. So that's the value for X. For these calculations, the target information may be provided directly. For example, as opposed to providing the thickness and the density, one may be provided the number of atoms in the target or the mass of the target that is being bombarded. And the cross-section, again shown here, has a value of 1 barn. 1 barn is 1 times 10 to the minus 24 centimeter squared. Continuing with the example of the production of astatine-211, based upon the conditions used at the University of Washington, the decay constant for the astatine-211 isotope needs to be determined. The data from the chart of the nuclides show that the half-life is 7.21 hours for astatine-211. Converting that into the decay constant is simply log 2 divided by the half-life. Remember that the half-life should be converted into seconds, so it's 7.21 hours with 3,600 seconds per hour. You get a decay constant of 2.67 times 10 to the minus 5 inverse seconds. For this example, calculate the production of astatine-211 atoms for a 3-hour irradiation. Again, 3 hours, convert that into seconds. 10,800 seconds, set that as time t. So for the two examples, let's do the production. For no decay correction, the atoms of astatine-211 is equal to the equation we've shown before. And since it's a production rate that is not decay corrected, we'll just multiply it by the number of seconds for the irradiation. And we're going to set that equal to N1 as a comparison point. N1 is equal to particles per second times the atom density times the target thickness times the cross-section times the time. And those values are shown here with the particles per second, atom density, target thickness, cross-section from the previous slide, and the irradiation time provided above. One gets the production of 1.3 times 10 to the 16th atoms of astatine-211, and that's equal to 3.5 times 10 to the 11th becquerel, and that's simply found from activity equals lambda n. Comparison to the decay corrected equation, which is shown here, substituting the terms and the addition of the decay constant. The equation terms are shown here using, again, the same terms as the non-saturated equation with the addition of the decay constant and the saturation term. One gets the production of 1.2 times 10 to the 6th atoms of astatine with an activity of 3 times 10 to the 11th becquerels. And we see that the decay correction shows that the amount of astatine produced is reduced since the irradiation is for 3 hours. The half-life of the astatine is 7.2 hours. They're on the same order. This is a demonstration that both equations can be used. However, the decay correction equation certainly is the suitable equation for this condition based upon the half-life of the produced isotope.
We now have an opportunity to take these equations to calculate growth and decay and use them to explore how we can determine the age of materials based upon naturally occurring radionuclides. So there are two sets of naturally occurring radionuclides, let's say primordial radionuclides, that have survived since they were first deposited on Earth. They tend to have a half-life of greater than 1 billion years. They also have decay products that are formed from these long-lived radionuclides. We saw the example of uranium-238, uranium-235, thorium-232 are also decay chains. And here's an example of potassium-40. And again, I wanted to point out from the chart of the nuclides, this black bar here designates that it's a naturally occurring radionuclide. In this case, long-lived. Potassium-40, any potassium-40 that was originally deposited on Earth 1 billion years ago has gone through on the order of 1 half-life. The age of the universe, nominally 4.5 billion years. The potassium-40 has gone through a half-life, but there's still a reasonable amount of material. Now, there's also shorter-lived radionuclides that are formed from continuous reactions with cosmic rays and with matter. So, for instance, tritium, carbon-14, beryllium-7. Here's the data from the chart of the nuclides for carbon-14. Its half-life is 5,000 years. Obviously, if any carbon-14 that was originally deposited on Earth during the formation 1 billion years ago has long since decayed. But these nuclear reactions, and for carbon-14, neutrons hitting nitrogen-14 produce a proton and carbon-14. And these reactions, there's also a reaction for producing carbon-12, but this reaction, as you can imagine, this is a neutron with sufficient energy to knock out a proton. This reaction occurs because the atmosphere is primarily nitrogen. Most of that is nitrogen-14, so this is our target. The neutrons are formed from cosmic rays coming in, forming these neutrons in nuclear reactions, and those neutrons then hitting the nitrogen-14, liberating a proton, and forming this carbon-14. Now, anthropogenic radionuclides have also been introduced, so radionuclides made by human activity. These are primarily actinides and fission products. They also include carbon-14 and tritium, and these have been introduced through weapons testing. All these radionuclides, particularly the naturally occurring ones, can be used to evaluate dating. However, if one is going to use carbon-14 or tritium, or anything that was introduced through anthropogenic activities, a normalization has to occur for accurate dating of these materials. So if we have a long-lived isotope that decays to some
Ground state or stable progeny or long-lived progeny.
we can use this as a clock to determine the age of something. And the clock is basically from this equation where the number of atoms at a given time t is just equal to the number initial times e to the minus lambda t. So let's rearrange this equation and solve for t, and the equation becomes what is shown here, where it's equal to the natural log ratio of the initial and the number of atoms at time t, and the decay constant of what's decaying. This doesn't really seem to help because it implies that we need to know the number of atoms at time 0. I can measure at time t. If I know what isotope is decaying, I've got the decay constant, I just don't know this value. We need to be able to determine what this time t is, and what we can say is that, well, the decay of the parent
To the progeny is constant.
and let's just say the
Total amount of progeny
plus the total amount of parent at time t is equal to the initial amount of parent. And all we're saying is that we can determine the amount of the parent, so this n naught value, based upon what we measure
currently for the amount of daughter and the amount of parent present. For the nomenclature, we will use P for parent and D for the progeny. D, daughter in this case, but we'll state it as progeny, but for the progeny, the term will be D. We can start with the equation where the amount of parent at time t equals parent initial e to the minus lambda t. We use the conditions where there is no progeny present at time 0. All the progeny is due to the parent decay, and no progeny is lost during the time of decay, so this time t. We can rearrange this equation so that the progeny at time t is equal to the parent initial minus the parent at time t. This becomes the parent at time t times e to the lambda t minus 1. And then solving for t, we rearrange this equation to what is shown here, where t, the age of the sample, is equal to 1 over the decay constant times the log of the sum of 1 plus the ratio of the progeny atoms to the parent atoms.
So let's consider how this could work. Imagine that there's a mineral, for instance, zircons, which are zirconium oxides, have a small amount of uranium embedded in them. One can evaluate these zircons, look at the amount of uranium-238.
And the progeny we're talking about in this case is lead-206.
Now, if you look at the decay chain, that's not a direct decay. There are many decays. But fundamentally, if you look at the half-lives of the isotopes between uranium-238 and lead-206, most of them are relatively short-lived compared to the half-life of uranium-238. So in essence, we just can take the uranium-238 half-life
as a decay directly to lead-206.
So what we need to assume is that there was no lead-206 present at time 0 in this zircon. All the lead-206 that is there is due to the decay of uranium-238, and that no lead-206 was lost during the lifetime of this material. What you could do for lead, if you were to evaluate if there was other lead present, lead has other stable isotopes, you could determine how much lead there is. Look at, for instance, lead 208, how much of that was there. And if you don't see the lead 208, convinced that lead is only from this decay. Also, the isotopics of the lead will show you that information. Of course, if there's uranium-238 present in your sample, you're probably also going to have uranium-235.
And those progeny will also need to be considered.
So if we go through this, what is the age of the mineral? Let's substitute our terms into this equation. So it's the decay constant,
which is
log 2 divided by 4.5 billion years.
The log of the sum of 1 plus the ratio of the progeny to the parent.
And I said that the fraction is shown here, the ratio. So we can just take those values.
At time 0, the progeny isotope lead-206 is not present. At time t, which is now, the progeny to parent ratio is 0.4.
So this becomes the inverse of the decay constant times log of 1.4, and you get 2.2 billion years. That's a relatively consistent time frame for some zircons, and this technique is actually used for dating older zircons. Again, we use this equation. This is our fundamental equation. All we need to know is the decay constant
and the ratio of the progeny and the parent today.
Carbon-14 dating is a little bit different. This is based upon the uptake of carbon-14. So
for carbon-14, the half-life is around 5,700 years. This is a good time to show some variation in literature data. There are 3 half-lives for carbon-14 shown here, 5,715 years from the chart of the nuclides, 5,730 years from the table of the isotopes, and 5,700 years from the Brookhaven website. The choice of the half-life will have an influence on the calculated age of the sample. So if one ever evaluates literature, you should make sure you explore and understand which reference was used for the carbon-14 half-life. For carbon-14 dating, the baseline is that an organism, as it's alive, is taking in carbon. The ratio of carbon-14 in natural carbon is constant, and it's due to the natural formation of carbon-14 in the environment. Dating with carbon-14 is based upon when the organism stops uptake of equilibrium carbon-14.
That organism is no longer taking up carbon upon its death, or it ceases that interaction. So the carbon-14 begins to decay. If I know the amount of carbon-14 in a certain amount of carbon at equilibrium, so at time 0, and I see how much carbon-14 there is per a unit mass of carbon at the current time, one could measure the sample age. We just rearrange the equation we used previously. 1 divided by the decay constant of carbon-14 times the log of the carbon-14 at equilibrium divided by the carbon-14 in the sample. So the equilibrium value is listed here. And what's the age? There's a wooden sample that's been found. It now has 0.15 becquerel per gram. This is 227 becquerel per kilogram, so we need to make it per gram, so it's 0.227 becquerel per gram. Let's rearrange these equations, and we get the natural log of 0.227 divided by 0.15, and we get 3,420 years. So carbon-14, 5,000 year half-life, is reasonable for doing carbon dating on that order, so thousands of years. There's actually another way that you can do carbon dating as opposed to looking at the radioactive decay. You can use a mass spec and count the number of carbon-14 atoms in a carbon sample. So you get that ratio, right? The activity is fundamentally using activity equals lambda n. I can get the number of atoms of carbon-14 per the number of atoms of total carbon. if I use the mass spec, I can actually count them. And you can go to actually lower detection limits. And that's one of the methods that is used today. And again, it's the same equation that we talked about previously, but now it's specialized for normalization of carbon-14 at equilibrium. And the equilibrium value shown here, again, this is listed in becquerel per kilogram. If your data is provided in grams, you need to change that normalization. These dating equations can also be varied to evaluate some conditions to understand the age of certain objects. So for instance, we can use an example as the Ocol reactor. This is provided on page 40 on the chart of the nuclides, some discussion of the Oclo reactor, and you can look it up online. But the Oclo reactor was a natural reactor that operated a few billion years ago. So we can use the dating equations that we just provided to kind of get an idea of what would be a reasonable time for that natural reactor to have been fissioning. This was actually determined when uranium samples from an area were evaluated, and the uranium-235 concentration in those samples was found to be lower than expected. This lower amount of uranium-235 indicated that it had previously fissioned, and they also saw some evidence of some fission products. So it indicated that at one time, the configuration of this natural ore body was sufficient to create natural reactor. And you can read about the details of this. So let's figure out a route of rearranging these equations to determine what was the time that the Oklo reactor was operating. Let's use the amount of uranium-235 as an indicator. Today, 0.7% of uranium is 235. And if we look at a reactor with light water, with regular water, the uranium-235 needs to be at 3.5%. The half-life of uranium-235 is shorter than the half-life of uranium-238. So fundamentally, there's a clock set up that if we know the uranium-235 to 238 isotopic ratio today, and we want the amount of uranium-235 to be 3.5% at time 0. So let's compare the 235 to 238, and we'll call it this uranium ratio, and use our regular decay equation. So we need to just set up the ratios. So the ratio of uranium today is equal to the initial ratio times, we got to take the decay constants for the 235 and the 238, since we're using a ratio of 235 and 238. The time is equal, it's the same. Let's rearrange this equation so that the amount at time 0 is just equal e to the minus lambda 235 times t plus lambda 238 times t. So now we have everything we need to know to solve this equation. We just rearrange, we solve for time. We have the ratio at time t, the initial ratio. We know the decay constants. We rearrange this equation, and we get a value on the order of 2 billion years, which is actually pretty accurate. So again, we input the ratio from today, input the ratio that we know that's a condition for the reactor to operate, throw in the constants, calculate, and we get a reasonable value. And all this was done is just based upon understanding that a reactor needs about 3.5% of uranium-235 with natural light water in order for fission to occur. The topics for Lecture 3 on decay kinetics include utilization and understanding of our basic decay equations, relationship between half-life and lifetime, understand relationships between count time and error, again understanding that the larger your counts, which would influence count time, you can have a reduction in error. How to utilize equations for mixtures, equilibrium, and branching. We introduced cross-sections and performed calculations using cross-section data. We utilized dating equations for isotope pairs. And we also utilized data from sources. Now, the one thing I want to point out is that in the example of carbon-14 on the previous page, 2 different half-lives were shown. And this actually comes from the fact that depending upon the source, this is the chart of the nuclides, this is the table of the isotopes, I can get different half-life data. So sometimes when I mention, if I provide a question, the answers may be different, and it could be down to the source of the data. I can normalize this by providing you the information or providing the source on a question, but just because there's differences, particularly slight differences, it could actually be from the data sources. So often, as you would do in research, you would reference the sources in which you obtained your data. So let's review some questions you should be able to answer based upon the lecture. What is the equation that is used to determine the isotope amount at a given time? That's a very fundamental equation, and the basis is shown here, where the n is the number of nuclei at either the initial or at the given time, lambda the decay constant, and then t. This also works for activity or counts or mass. It could work for concentration if the volume doesn't change. What is the equation for the decay constant? This decay constant here, very important term, is log 2 divided by the half-life. One thing you need to make sure is your half-life given in a time unit needs to match the time unit that you would use in this equation. So in this equation here, you have time here in a given unit. The decay constant needs to have that same time unit, obviously from the inverse. What equation is used to find the activity? Again, the decay constant times the number of atoms is equal to activity. This would be counts per whatever the unit is. That's why we often use the decay constant in seconds. So then if I were to do this, I'd get the activity in becquerel, counts per second. And what's the relationship between standard deviation and the number of counts? Well, it's just the square root of the number of counts, and the error is the inverse of that value. Very important term in terms of setting up and performing experiments. Some other questions you should be able to answer. What's the activity of a nanogram of a certain isotope, in this case actinium-225? The main equation to use, activity equals lambda n. So now we need to solve for n for 1 nanogram of actinium-225. We can evaluate that number. We want to get the decay constant for actinium-225. The decay constant's in days, convert that to seconds. Log 2 divided by that, we get a decay constant. Now we plug those values in. Activity equals lambda times n. And a nanogram of actinium-225 is about 1,000,000 becquerel. And that's close to what's used in medical applications of actinium-225. It'll be, let's say, from 1 to 10 nanograms. So 7 days later, what's the mass of that actinium? Well, the mass at time t is equal to the mass initial times e to the minus lambda t. We will utilize this equation. The 1 nanogram, e times e to the minus lambda t, is equal to 0.616 nanograms. So 10-day half-life, 7 days later, not quite half of it is decayed. For making actinium, you can use an isotope of thorium, thorium-229, that decays to radium, and then that radium then decays to actinium. So let's ask the question, if I have some thorium-229 and it's decaying, it has an activity of 1,000,000 becquerel. What's the activity of the radium-224 after purification? So we start off with no daughters, just the thorium-229. It starts decaying, and at 4,000 hours after the purification, it's reached equilibrium. So we see that the radium grows in, and you can determine that at this point the amount of the activity of the radium is equal to the activity of the thorium. So it's a parent-daughter relationship. And we solved this using the ERG program. Other terms, conditions, questions you should be familiar with. What's a becquerel? Well, becquerel is decay per second. A curie, what's a curie? 3.7 times 10 to the 10th decays per second, and a curie comes from a gram of radium. What's a reaction cross-section? It's the probability of a nuclear process. The value is in barns, where one barn is 10 to the minus 24 centimeters squared. So how can you determine a neutron flux in a reactor if you irradiate a certain amount of material for a given period of time? In this case, let's use the irradiation of a wire of cobalt-60, 500 milligrams of it for 1 hour. Just use this equation where the activity you can measure it, you can pull out the cobalt, measure it, the activity is equal to the amount of the cobalt-59. And what cobalt is made from this? Cobalt-60, because we're just adding a neutron to it. I measure the activity of cobalt-60. I know the amount of cobalt-59. I know the cross-section. This is not known. The decay constant for the cobalt-60 is known, and the time of the irradiation is known. So I just rearrange this equation, and I get the flux.
What are the basic assumptions in using radionuclides for dating? These relate to the progeny. One is that no progeny atoms are present at time 0. All the progeny that are present in the sample at time t are due to the parent decay, and no progeny is lost during the time of the decay.
All these equations can be used to develop some Excel spreadsheets that can provide calculations. So for instance, and this is not an assignment, this is just if you were to do further work within radiochemistry, you can develop Excel spreadsheets where you can input some data like the mass or the mole of a certain isotope and determine the activity. You can get a concentration, and if I knew the volume of a certain amount of isotope, I can calculate the activity. So for instance, if I knew that I had a solution that was a micromole of plutonium-239 and it was 1 milliliter, I could calculate the activity of that 1 milliliter solution. I could make a spreadsheet to calculate the isotope production from radiation.
And one can do some calculations on parent progeny decays.
So for instance, uranium-239 going to neptunium-239 going to plutonium-239.
When you have completed this lecture, please comment on the blog and respond to the Lecture 3 quiz. The lecture summary, those terms and concepts that you should focus on from the lecture, are shown here. The error in counting is an important term that was discussed, and it's simply the square root of the number of counts. This dictates conditions when one does work with radioactive material. There were a number of examples of utilization of equations of growth and decay. Examples include determining the number of atoms at time t from an initial amount of atoms using this equation, the activity from the number of atoms and the decay constant. This is a very fundamental equation, activity equals lambda n, and the relationship between half-life and the lifetime. This shows that the average lifetime for an atom is a little bit over the half-life. You should be able to calculate parent-progeny relationships. The full equation for the parent-progeny relationship is provided here, where the progeny atoms at a given time are a function of the amount of initial parent and any initial progeny present. Relationships were also presented that can simplify this equation based upon the half-lives of the parent and the progeny. You should be able to do calculations for multiple progeny using programs and understand that the Bateman equation is used to do multiple progeny. However, you will not be asked to calculate the Bateman equation or develop programs or spreadsheets for doing the Bateman equation. You should understand branching decay, that isotopes can decay by more than one decay route. Often this is not the case, however, there are examples that were presented and that we'll discuss later in the course. You should be able to use the branching ratio for mixed decay to find the partial half-life of a given decay. So for instance, with bismuth-212, which decays by alpha and beta, the data shows a half-life for bismuth-212 You can use that to determine a decay constant for bismuth-212. However, the partial half-lives or the partial decay constants for the alpha decay and the beta decay are based upon the branching ratios. For isotope production, you should be able to use cross-sections for isotope productions and understand there are different equations for reactors and accelerators. And you should be able to include the saturation term that accounts for the decay of produced isotopes during production. Finally, this lecture discussed age dating using isotopes. You should be able to understand what are the necessary conditions for dating to be successful and what equations can be used for this, particularly the different equations